Hi everyone, welcome back to our video series. Today we will talk about the discretization of a rectangular domain for your 2D finite elements project. As we did in our previous session, we will focus on these two elements, so the constant strain triangle and the bilinear quadrilateral element. And we will have a rectangular domain like this. Its width will be d1 units and its height will be d2. And we will divide it into p elements on its width and m elements on its height. Okay, so just as an example, for the quadrilateral element, we will have a domain like this. And the same domain for the triangular element. Okay, so let's start looking at our code. So we have two .m files here. The first one is our runner, so it's just to run the uniform mesh function we are going to look at. And up until this point, so here is our actual runner, and the rest is, just plotting. So I won't actually go through that because you did learn how to plot nodes and elements and their labels in your previous project. So we will just use them for visualization. Okay, so let's start. So again, we start with CLC clear all CLF. This CLF here is, it clears the figure. So I actually have figures here that we will generate. And I don't want the window to close up, so that's why I use that instead of close all. So it's not something new. Okay, so let's look at the parameters we have. So as I said before, d1 is the width, d2 is the height, and p is our increments along our width, and m is our increments along our height. And here we assign our element type, so it can either be d2 tr3n or d2 qu4n, and we will start with the four-noded one. And this r, it's just commented out, it will come into play later when we have a void mesh. So first we start with the uniform mesh, and then we will have a circular void inside a rectangular mesh. So that's when we have this r here. So today we will just look at the uniform mesh, and you can see that it takes these as input and the element type, and in return it gives us the node list and the element list. So let's actually see what we run, or let me run something nicer looking. Okay, so for this particular domain, let's see our node list. As in our previous videos, the node list stores the x and y coordinates of every node. So the first column is the x coordinates and the second column is the y coordinates. And so if you look at the first node, it's 0 and 0. It's at 0 and 0. And I don't know, the 20th one, it should be 1 and 1, right? 1 and 1. So this is our node list, nothing new here. And our element list, now it stores the information of the node information of particular elements. So the first row corresponds to the first element, and I don't know, the 8th row should correspond to the 8th element. You know all this already. And these four are the four nodes of the element. However, the important thing here is that we need to follow this counterclockwise direction when we are constructing our element list. Okay, so if you look at it, the first element is composed of node 1, 2, 7, and 6. And it should be in that particular order. So 1, 2, 7, 6. It could have been 2, 7, 6, 1, 2. I mean, it's still counterclockwise. So that would work too. So the important thing is that they should be counterclockwise. And again, for example, element 4, it should be 4, 5, 10, 9. 4, 5, 10, 9. Okay? So this is what we want to do today. So let's go into our uniform mesh function and see what it does. So we start with setting our problem dimension to 2. You can also read your problem dimension from the type of element you input, but since we are just looking at two-dimensional elements today, we just set it to 2. And then now we have something called Q here. So what is this Q? This Q stores the information of the corners of your domain. So let's go back to our slides. And so this corner of the domain, we want to fix it to 0. Well, not fix it. We want to put it to 0 and 0. Okay? And then this corner would be at D1 to 0. This one should be at 0 to D2. And this one would be at D1 to D2, right? So this is what we have. This is the first corner, this is the second, this is the third, this is the fourth. The ordering is not important because this is not an element, mind you. This is just the corners of our domain, and we will know where we assign which corner to. So, and we didn't have to do that. We could have. This is just for convenience later. So let's take a look at our number of nodes now. So if you're dividing our domain to m rows and p columns, we would have p plus 1 times m plus 1 nodes, right? Because let's see, we have m plus 1 rows here, right? So m is 3, 1, 2, 3, 4, m plus 1 rows. And similarly, p is 4, 1, 2, 3, 4, 5, p plus 1 columns of nodes. So this is a number of nodes. And for number of elements, we just say p times m because we are dividing it to p columns and m rows. And we set our node per element to 4. And we do that because, well, it will change according to our element type. So the 3 node should have 3, right? But however, we want to use a 4-noded element to generate the 3-noded one. And you will see how we do that later. So that's why we set it to 4 and forget it for now. So let's look at the generation of our nodes then. As usual, we start with the initialization of our node list. So it's zeros, number of nodes times PD. This is nothing new. And then we have two constants here, the A and B. So what are these A and B? So A is D1 over P. So it's the length or the width of these increments, okay, along X. And similarly, B is D2 over M. So it's the length of these increments along Y. Okay, and we need that because of the method we use to generate our nodes. So what we will essentially do is we start with our first node on this corner, and then we say, well, the second node should be whatever this increment is times 1 plus the x coordinate of that. So that one was the 1 over p, I think, A, yes. So this should be the x coordinate of node 1 plus 1a. This should be the x-coordinate of node 1 again plus 2a and so on. And similarly we have the same logic but in y direction now. So this should be the y coordinate of node 1 plus b. And this is plus 2b and 3b, so on. Okay, so this 2 for loops here do that. So as you can see, we have a loop over I from 1 to m plus 1. So m was our number of, m plus 1 is our number of rows in terms of nodes, right? We have m plus 1 rows of nodes. So, and we have a loop over j from 1 to p plus 1. And that is our p plus 1 is our number of columns of rows. Okay, so when j is 1 and p is 1, we are looking at the first row and the first column of our node. So we are looking at node 1. You can think of it like that. And when m is 1 and p is 2, when the loop over m plus 1, so I is 1 and p is 2, we should be at node 2, right? That's how it works. And then we have our n here. This n is just a counter, so we set it to 1. And then at the end of each iteration, we add 1 to it. So in our first iteration, we are looking at the first row, so the first node of our node list, and then it becomes 2. In the next iteration, we are looking at the second node, and so on. Okay, and let's see actually what we do. So we say that the first column of that specific node, so the x-coordinate of that node, should be q11. So what was q11? It's the first column of first row, so the x-coordinate of this corner, right? That thing plus j minus 1 times a. So this j minus 1 basically counts our columns. So when j is 1, we are looking at the first column. This thing becomes 0. This is exactly what the x-coordinate of that corner is. And when it's 2, we are looking at this one, the second column. And we add j minus 1, so 1 times a to it, and so on. And for the y-coordinate of the node, we have the same logic. It's just now we are looking at the y-coordinate of that node, of that corner. And then we are adding it I minus 1 times b. So remember, I is counting our rows. So row 1, row 2, row 3. And b is our length along y. Length change along y. Okay. So this is how we generate our nodes. So we can actually move on to the element generation now. So now we have our node list, and what's left to do is just assemble the elements. So like we had previously for our node generation, we have 2 loops here, but this time they're from 1 to m and 1 to p instead of 1 to m plus 1 and 1 to p plus 1. And the reason for that is now the number of rows and columns, they switch to m and p. For elements they were m and p, right? For node they're m plus 1 and m p plus 1. So again we have that, and so let's just forget about this thing and take a look at what this does, and we will go back to this after that. So what we want to do is, if you somehow have the information of the first element, if if you somehow have the information of this element, using that information, you can generate the second element and the third element and so on. So what this part of the code does is it uses the information of the previous element to generate that element. Okay, so don't look at this index. It's just an index. So we are at some element. So let's say it's element 2. Okay, and the first column of element 2, so the first node. So we're looking at this node, right? It is, in fact, the second node of the first element, right? So this is the first element. This is first node, second node, third node, fourth node. So the second node of the first element is the first node of the second element. Okay, and this is what we do here. So the first node of the particular element we have is the second node of the previous element. So these are the same indexes. It's just this one has -1. So it's looking at the previous element. And then similarly, the fourth node of the second element, so 1, 2, 3, 4, is actually the third node of the first element, so 1, 2, 3. And on this line here, we have that. So again, we have an index, node 4 is equal to that index -1, the previous element, node 3. Okay. And using node 1 and node 4, we can get node 2 and node 3, because node 2 is just node 1 plus 1, and similarly node 3 is just node 4 plus 1. And you can see that this holds for every element. So here we just have that. So node 2 of that specific index is equal to, again, that specific index. So we don't have a -1 anymore. The first node plus 1. And similarly, the third node is the fourth node plus 1. Okay? So this part of the code does that. But in order to be able to do that, we need to have the information of the first element of every row, right? So this part of the code gives us that information. So let's see what it does. Well, firstly, we say that we see that there's an if condition, and it checks if j is equal to 1. And remember, j is from 1 to p. So j counts our columns, right? So if j is equal to 1, we are always looking at the first element of a particular row. So if I is 1, we are looking at the first element. If I is 2, we are looking at 5. If I is 3, we are looking at 9. Okay? And so we can actually take a look at the indexes now. So you will see that this I-1 times p plus j, what it does is, so I-1 plus I-1 times p, it lets you skip I-1 times rows. So because at every row we have p elements, so right, in this case our p is 4 and we have 4 elements in each row. When I is 1, this thing becomes 0, so we don't skip any row. But when I is 2, we should skip 1 row, right? We should be here. So this becomes 1 times p. And to be here, we also need the plus j. So when j is 1 and I is 1, we are at 1. J is 1, I is 2, we are at 5, and so on. Okay? So this is how all of these indexes work. They're the same. And what happens here is that we start with the first node. So that node itself should be I-1 times p plus 1 plus j. And you can see that it's almost exactly the same as this thing. The only difference is that this p becomes p plus 1. Why? Because we are now looking at nodes, right? And at every row, we have p plus 1 nodes. So now we have skipped p plus 1 nodes. Okay, so when I is 1, this thing becomes 0, and our j was 1, so we are at node 1, right? And if our I was 2, we should skip p plus 1 nodes. So p is 4 plus 1, 5, plus j, 6. This is how we find the first node of these elements, okay? These first elements of every row. So once you find the first row, a node, the rest is easy. So again, the second node is just that node plus 1. So you will see that these things are exactly the same. So our second node is our first node plus 1. And for our fourth node, we say that, remember this skipping logic we had? So we have that same thing. So when you're looking for the first node of an element, we have this thing, right? For the fourth node, it should skip p plus 1 more, okay? So this I minus 1 should just be I now. So this is exactly what we have here. But and we don't have to write it like that. We can also write it like the node we have here plus p plus 1. So we have skipped p plus 1 here, okay? So p was 4, right? So 1 plus 5 is 6. And lastly, using our the information of the fourth node, we just add 1 to it to get our third node. And that is how we assemble our element list. So we're almost done. What's left is the actually assembled element list of a three-noded triangular element. So the thing we do for that is, so these two domains that I go back and forth, and they have the same D1 and D2 and M and P, but they just their element types are different. So you can see that they all have 20 nodes, right? So their node number hasn't changed. What we do is we just divide the existing 4-noded element into 2 triangles to achieve the triangular domain. Okay, that makes our job very easy because we don't have to write everything again. We generate the same nodes, we generate the same elements. We just do something a little modification here so that we divide our 4-noded elements into 2 and get our triangular elements. Okay, so let's see what happens there. So we have an if condition, and it checks if our element type is equal to the 3-noded triangular one. And if it is, then it goes on to define a new node per element. So remember, it was set to 4. Now we set it to 3, and we say it's a new node per element. And we generate a new element list. So we initialize a new element list called EL new. And that is, it should be 2 times the original number of elements. So the number of elements the quadrilateral domain had times 2, right? Because we're dividing every element into 2. We should get twice the number of elements. By node per element new. So this time in our element list, we should have 3 nodes per element. So that's how we initialize our new element list. And then we have a simple for loop from over the number of from 1 to number of elements, and this number of elements is again the original number of elements we had, so the number of elements of the quadrilateral version. And then for each element, for each original element, we go by dividing it into 2. So what we do here is, let's first check the actually how we, or maybe let's look at the index first. Sorry. So this 2 times I minus 1 plus 1. So when I is 1, this thing should be 0 plus 1, 1, right? So for the first original element, this thing is 1. And then if you look at this one now, this is that thing plus 1, right? So this thing should be 2. So for element 1, the old element 1, we now have the new element 1 and element 2. Okay. For element 2, we should have 3 and 4. And let's see if we do have that. So I is 2 now. 2 minus 1. 1 times 2, 4. Times 2, 2. Plus 1, 3. And plus 1 to that is 4. So that's how we number our new elements. And to assign the nodes of the new elements, we again use our old element list. So this is the first element of the pair, right? This is always the first. So this is either 1, 3, 5, 7. And this one is 2, 4, 6, 8. Okay. So we look at this and we say, well, the first node of this triangular one should be the first node of our original quadrilateral one. So this was 1, 2, 3, 4. 1, 2, 3, okay. So the first node of our new element should be the first node of our old element. So I corresponds to the element we had originally, right? And the second node should be the second node of our old element. And lastly, the third node should be the third node of our old element, right? Because 1, 2, 3, 4. This is very straightforward. And for the second one, again, we have our first node, the first original node of the element as our first node. So 1, 1. But our second node should now be the third node of the quadrilateral element. So the second one is assigned the third one. And lastly, the third node of our new triangular element should be the fourth node of our old element. So that's what we have here. Okay. So we do that for every single element we had in our old domain. And at the very end of our loop, but inside our if condition, we say our element list is the new element list we have. So we get rid of the quadrilateral one and replace it with this one. And our node list doesn't change. So this is how we generate our domain. So let's run it with different parameters and see. And maybe change our element type. Yeah, so see that our number of nodes didn't change, but we now have twice as much the elements we had previously. So this is how we generate a rectangular uniform domain. And next we will see how we generate a square domain that has a void inside of it. Let's move on to the generation of our voided mesh. So now we will have a again a rectangular mesh, a domain that also has a circular void inside. So it will be again d1 along its width and d2 along its height. And we will divide it into p elements along its both height and width this time. But the difference is now we divide it along its diagonal into m elements. Okay. And the end result we want to have is this. So let's see how we get that. So our runner is the same. We just now call on the void mesh function instead of uniform mesh. And we have a new input that is r. So let's go inside void mesh and see what it does. I actually want to open uniform mesh too, so that we can compare them, because there will be some similarities. Okay. So we again start with our cube. So remember, this stored our corners, the corners of our domain, and PD equals 2. And then we calculate our number of nodes. So let's go back to the slides. Okay. We want to divide our domain into 4 regions. So this will be region 1, this will be region 2, this is 3, and this is 4. And we will generate the node lists of each region separately and then combine them to get our general node list. So if we take a look at these regions, so notice that they share these diagonal nodes, right? And we don't want to generate the same node twice. So what we do is we say that the first region and the second region, they contain the diagonal nodes. And the third and the fourth do not so. Now from 1 to 52, well, I mean these nodes belong to region 1, and these belong to region 4, these belong to region 2, and these belong to region 3. You can see it here, so the red lines divide the regions. So regions 1 and 2, they have the diagonal ones, 3 and 4 do not. Okay, and so let's use that knowledge to calculate our number of nodes. So in region 1 and in region 2, we will have how many nodes? We will have p plus 1 times m plus 1 nodes, right? Because you can think of this, these two regions as what we had for the uniform mesh. It's just that they are warped on one of their edges. So this is quite similar to what we had in our uniform mesh. It's just warped along its top edge, right? So we would have p plus 1 nodes here times m plus 1 nodes here. And similarly for node 2, same thing. For region 2. And for regions 3 and 4, now we don't have the diagonal nodes, right? So this p plus 1 here, it should be p minus 1, because now we're subtracting 2 for each diagonal. So for regions 3 and 4, we should have p minus 1 times m plus 1 nodes. And that is exactly what we have here. So this 2 times p plus 1 times m plus 1, it covers nodes, regions 1 and 2. And this one, 2 times p minus 1 times m plus 1, it covers regions 3 and 4. Okay. And for number of elements, now if you again think of this as the uniform mesh we had before, every region should have p times m elements, right? So p is 3 columns of elements, m is 4 rows of elements, p times m times 4, because we have 4 regions. So that is our number of elements. And node per element is again set to 4 because we will first generate the quadrilateral element, and then we will do what we did for the uniform mesh. So we have the exact same code. So we will just divide our 4 noded elements into 2 triangular elements, and so there is nothing new there. That's why we set our node per element to 4. And we can now move on to the generation of our nodes. So we initialize our node list again, so number of nodes we had calculated before. And now we have our A and B. So this time it's D1 over P and D2 over P, because remember we're dividing both its width and height to P. And we can move on to the generation of the nodes in region 1. So, okay. This core 1,1 is what we call the node list of region 1. The small node list that we will generate. And we will have core 2,2, 3,3, and 4,4 for each region, and then we will combine them to get our node list. So as we do for our node list every time, we initialize it. So remember our discussion for our, the number of nodes. We said regions 1 and 2 have P plus 1 times M plus 1 number of nodes, and that is exactly here. And then we have 2 for loops here. And I actually want to show you what they do by plotting before explaining what they do. So let me copy and paste this node plotting function here. Oops. Okay, and this should not go to number of nodes, it can be this. Okay, and I want to stop our code here and run it. So, okay. So what we have here is first, this line you see, it corresponds to this line here. So the first for loop we have generates the nodes along this line. And then the second for loop we have generates the nodes along this line. These, okay? And the reason you'll see, well, a 16 here instead of 1 is, remember we initialized our core 11, core 1,1, but we didn't actually find the coordinates of the nodes in this region. So they are 0 and 0. So every node that we didn't find yet is plotted on top of 0 and 0. So this is what we want to do in these 2 for loops. And then here we will fill in the blank region. Okay, so let's see what these 2 do first. So comment these and this again. Okay, so we're trying to plot this, generate nodes of this region, and first we will generate these 4 nodes. So we have a for loop over I equals to 1 to P plus 1. Remember we have P plus 1 nodes here for regions 1 and 2. Okay, so then we, like we did for the uniform mesh, we use the coordinates of the corner. So the x coordinate of the first corner plus a, so I minus 1 times a. That's just what we had before. Okay, so and our y coordinate should be the same coordinate as our corner node, the y coordinate of the corner node. So this is just very similar to what we had in the uniform mesh, so I'll move on. And then now we have the nodes here. So this is actually, it's still the same logic. It's just now we have a circle here. So the increments A we had here, they should now be angles, right? And we go to our slides again. You can see that this angle right here, it's pi over 4, right? So we know that the starting point of our of this line here, it should be 1, 2, 3, 4, 5. So 5 times pi over 4. And then it will go along this arc, which is pi over 2, so that such that we divide pi over 2 into p now. Just like we divided d1 to p, our increments will be pi over 2 over p now. So we will go over the angles. Okay, and this loop does that. So it starts from I and goes to it starts from 1 and goes to p plus 1. Why? Because we have p plus 1 nodes here, right? And let's first look at the index here. So we have m times p plus 1 times I. Why? Because we have let me actually go to this. We have m rows of nodes up until here, right? So to get to this, we will need m times p plus 1 plus 1. For this plus 2, for this plus 3. So I covers the columns again, and we skip m rows by doing m times p plus 1. So we are looking at this node here when it's I is 1. So we are looking at its x coordinate and its y coordinate, and let's see what we have. So we have r cos 5 pi over 4. So remember what we had. This is pi over 4, so 1, 2, 3, 4, 5 pi over 4. We start there. So the cosine of that pi over 4 is our x coordinate, right? Plus, now we add our increments for every node. So at the very first node, we don't add anything, so I minus 1 is 0. And the second node, now we should have add pi over 2 over p, right? Because all of this arc was pi over 2. So when I is 2, now this thing becomes 1, so we add 1 increment. And then we do that for every node on the loop. And there is also this d1 over 2 here. And that is because, well, this coordinate we have calculated here, that works only if this circle is, its center is at the origin. So we know that it's not, it's actually at d1 over 2 to d2 over 2. So to its x coordinate, we should add d1 over 2. And then for the y coordinate, you will see that we have the same expression. This time it should be the sinus, and we add d2 over 2 because it's on d2 over 2 on y. So this is how we generate the nodes on this line. Okay. And once we generate these two lines of nodes, we can then use those to generate the nodes in between. So these two for loops do that. So let's see how they do that. First, we have a loop over 1 to m minus 1. So remember, we have m plus 1 rows of, these are rows of nodes in my mind, so that's what I call rows. We have m plus 1 rows of nodes here. However, we have generated 2 of those. So if we subtract 2, we get m minus 1. And then we still have every column of nodes, so it's still p plus 1. So we have these two for loops. And then I want you to take a look at the node generation we had for our uniform mesh. So we always add our increments times something to the initial coordinate of the corner. We do the same thing here. It's just these A's and B's we had in our uniform mesh are now changing. So for every row, we have different dx's. So the increment between the on the x between the nodes. And then for every column, we have different increments along y. So we need to calculate those at every for every row, for every node. So this code just does that. So at the very start of the loop, we always calculate our dx and dy. And what we do for that is, so if you're looking at node 13, for example, this node here, where we should, for the x increments, we should calculate the difference between these two nodes. And then divide it by m, right? Because we have m elements here. Well, not elements, let's say m increments here. Okay. And then similarly, for the, we do that for both x and y coordinates. Okay, so this core m times p plus 1 times j, this thing brings us to this coordinate, this node. So remember that m times p plus 1, we had m plus 1 rows of nodes here. So m times p plus 1 should bring us to the end of this row, plus j, we are here now, minus j, comma 1. So j is just 1. Okay, so this part does exactly that. So we have the same thing for dy, but for dx, we were looking at the x coordinates. For dy, we are looking at the y coordinates. So this thing brings us to this node, the x coordinate of this node. This thing brings us to the x coordinate of this node. We take their difference and divide it by m. And we do the same thing for the y coordinates on this line. And then what's left to do is find the coordinates in between these two lines using dx and dy. So core I times p plus 1 times j is, well, it's this thing, but now we don't have m, we have I, right? So we are looking at I at the end of the ith row. So if I is 1, at plus j, we're looking at whatever j is. So if j is 1, we are looking at this node. If it's 2, we are looking at this node, and so on. That node is equal to the previous, the node on the previous row. So I minus 1 times p plus j, and p plus 1. So if I is 1, and j is 1, we are looking at this node, and this thing is this node, right? Plus dx. And then similarly, again the same node, plus dy for the y coordinate. So these two lines let you check the previous line of the same node, so corresponding node on the previous line. So if this is this node, so this should be I equals 2, j equals 2, right? If I is 2, 2 times p plus 1 is we are here, plus j is 2, we are here, I minus 1 p plus 1. Now we should be here, plus j here. Okay, so we are checking the node at the previous line. Okay, so these are, I know, a little complicated maybe, but first of all, this is just one way of generating nodes. This is how I learned it. So if you can come up with a simpler way, you can implement that. But I think once you get this part, the rest is very easy. You'll do very similar things for the generation of nodes in the rest of the regions, and then you just merge them. So yeah. So we can move on to region 2 now. So remember, region 2 was this. So we do pretty much the same thing. So we just we first generate the nodes here. So I can actually plot that again, and we can see what happens. So let me do that. Make these maybe 2, 2. And run the code until here. Okay, so now we want to first generate this line of nodes and then this line. And then we do the same thing to fill out the rest. So again, if we compare it to core 1.1, we initialize it with zeros again. So it's the same thing, remember, because we had the same number of nodes. And for the generation of this line, the only difference is now we're looking at this corner. So we're looking at the x coordinate of this corner and then adding a's to it. Okay, so remember a was it's d1 over p, right? And our y coordinate is just what we had for the y coordinate of that third corner. Okay, so for the generation of the nodes on this line, the only difference is now it's our starting point, well, first, and then the direction we are moving in. So firstly, we start from this corner, and this corner is, now this was pi over 4, so 1, 2, 3 pi over 4. So we have 3 pi over 4. Now we are moving in this direction, so we should now subtract the angle increment. So minus I minus 1 times pi over 2 over pi p. So it's just what we had, but now we have a minus sign. And then again, it's cosine for our x coordinate and sine for our y coordinate. And we also don't forget to add d1 over 2 for our x coordinate and d2 over 2 for our y coordinate. So this is how we do that. And for the generation of the nodes in the remaining region, we don't change anything. So I actually want to just copy this and paste it here so that we can see them side by side. So you can see that there is nothing that changes other than now core 1 becomes core 2. And the reason for that is this dx and dy calculation we are doing, it's accounting for the sign changes. So what I mean by that is, for example, for region 1, we're moving along from left to right like this and upwards. So our x coordinate is increasing always, and our y coordinate is always increasing. But for region 2, our x coordinate is increasing, however our y coordinate is decreasing. But this code accounts for that because dy is this one, remember, it was the coordinates of the nodes along this arc. So whatever this is minus this is something that is negative. So that's how we account for the sign changes. So they are exactly the same, and we can move on to region 3 now. Okay. So there are little differences in region 3 and 4, and well, the first one is our number of nodes. So as we discussed in the beginning, they should be p minus 1 times m plus 1, right? Because we don't have the diagonal nodes anymore. Okay, and actually that is mostly what is different. And also we were going from left to right in region 1 and 2 in our node generation. Now we're going from bottom to top. Okay, so let's see, we initialize our core 3, and then we have a for loop over I equals 1 to p minus 1. Again, why is it p minus 1? Because let me run this thing again, but don't want this anymore. I want to see the whole domain. Okay, so so remember, we don't have these diagonal nodes, right? So what we have here is it used to be p plus 1, now it's p minus 1. So our for loops are from 1 to p minus 1 because of that. And then let me actually plot this thing again here. So oops. So we see what we are generating. These will be 3 now. And this should be minus 1. Okay. This is something interesting. Oh, no, this is correct. Okay, this thing here is just the 0 nodes we see. So, okay, this is correct. So we want to start with the generation of this node, and this corresponds to the first node that is here after the diagonal node. Okay, so the first node that is along this line. So that the x coordinate of that node will be the same as the x coordinate of this corner, right? So we just say that it's equal to q11. And the y coordinate, well, it should be whatever the y coordinate of this corner is, plus b. So b was our increment along this line, dt over p. So, but if we compare it with region 2, for example, it was I minus 1 times a. This time it's I times b, because that minus 1 made it such that at the first, when I is 1, at the first iteration, we are calculating the coordinates of the first node on the diagonal. Now we are skipping the node on the diagonal. So because of that, we add the increment for the first node we are calculating. Okay? That is pretty much the difference. And then we move on to the calculation of the nodes along this line. So these two. And you will see that now, again, if we compare it with our previous loops, again, it's instead of p plus 1, it's it's up until p minus 1, and then this here, it was m times p plus 1 times I. This time it's m times p plus 1 plus y, I. Because of the, again, because we are skipping the diagonals. So, and we're at region 3 now, and we're going from bottom to top. So we start from this angle, which is what? Pi over 4 times 1, 2, 3, 4, 5. So 5 times pi over 4 minus I times pi over 2 over p. So why is it minus? Because we are moving along this direction. And why is it I? It used to be I minus 1. It's the same reason this is also I and not I minus 1, because we are not looking at the coordinate of the node on the diagonal, we are looking at the next one. Okay? And then, as usual, we add our d1 over 2. And for the x coordinate, we are looking at cosine, and for y, we are looking at sine, and we have d2 over 2 here. Okay. So, let me comment this. And if we take a look at this loop here now, you will see that it is pretty much the same as what we had here. Let me again copy this so we can compare them. Okay, so again our loop starts from 1 to m minus 1. Why? Because along here, inside the region, we have m minus 1 rows. We have calculated these two. And now it goes until p minus 1 because we don't have the diagonals. And then notice that the only change here, apart from these 3 threes, is that these p plus 1s now become p minus 1s. Why? Because remember, these help us skip rows, right? And for regions 1 and 2, on every row we have p plus 1 nodes. But because we don't have the diagonal nodes on regions 3 and 4, we will have p minus 1 nodes on every row. Okay? And that is pretty much the only difference. So we again calculate our dy and dx. And as I said before, it takes care of the signs itself. And then we calculate our coordinates using the information of the node on the previous row. Okay. So let me delete this, and we take a look at region 4. So for region 4, it's again pretty similar to region 3. We have the same number of coordinates, the same initialization, and then we have again a loop until p minus 1. Now we're at region 4, and we're generating this line here. So our x-coordinate should be equal to the x-coordinate of the second corner of the domain. So that is what we have here. And then our y-coordinate should increase by b increments. So pretty much what we had for region 3. Okay, it's just our starting corners are different. And then we move on to the generation of the nodes along this line. So remember, we're going from bottom to top. So we're at here, which is now pi over 4 times 1, 2, 3, 4, 5, 6, 7. 7 times pi over 4. And we're moving along this direction, so we are adding our increments. So plus I times pi over 2 over p. And again, this is not I minus 1, this is I, because we are skipping the node on the diagonal. And lastly, we add our d1 over 2 and d2 over 2. So that is that. And to generate the remaining nodes, this is the exact same code as core 3.3. It's just we have changed these 3 3s to 4 4s because it's the same logic. Okay. So the hard part of the code is done. So what's left to do is now we have 4 distinct regions that we want to merge together to have a full node list. Okay, so I will actually plot these regions on the same plot so that we can see what is happening. Okay, so okay, do it here. So okay, we need 4 of them, and this is core 1 1. This is core 2 2. This is 3 3, and this is now 4 4. And 4 and 3, they should be p minus 1. These should be p plus 1. Okay, and let me stop it here. So let's run it. Continue. Okay. So now you can see the 4 regions distinctively. So this is region 1. So it starts from 1 and goes up until 20. And region 2 starts from 1, goes until 20. Region 3, 1, 10. And region 4, 1 to 10. So what we want to do now is we want to take each row of every region. So this is the first row of region 1. This is the first row of region 4. And this is first row of region 2. And this is the first row of region 3, right? We want to take them and append them together. And we do that for every row. So once we're done with first row, we move on to the second row of the first region, and second row of the fourth region, and so on. But the only problem here is, well, it's not a problem, but something we need to address is, you can see that the order of the nodes on region 1 is fine, so it goes from 1 to 4. And region 4 is okay as well. However, for regions 2 and 3, it's backwards. So we need to take care of that. Okay, and this for loop here does that for us. So the fan of my laptop was acting up, so I hope it wasn't very audible. So I had a brief pause because of that. So we were looking at this loop. So as I said before, this loop does the appending of the rows of the different regions for us. And so I also want you to think of this as a uniform mesh that has been twisted such that its end is touching its beginning. So let me actually plot it for you. But first, see that if you think of this as a uniform mesh, it would have m increments along its height and p times 4 increments along its width, right? Because we have 4 regions. So let's actually run that. So 4 times p, and let's call the uniform mesh function and run that instead. Okay, so what happens is this edge has been rotated such that it is now touching this edge. Okay, and because of that we have 4. Well, let me again plot this version, the void version, and then explain it from there. So so I forgot to remove this 4, and let me also remove this one from there. Okay, so what we want to do is we want to take the first row of first region and then add to it the first row of the second region, the fourth region, and so on. So we have a loop over 1 to m plus 1. So because we have m plus 1 rows of nodes, right? And then what we have here is this should be every node that corresponds to the first row of every region. So the nodes in the first region plus this, plus this, plus this, okay? Here we should have the number of those nodes. So, well, let's see. This I minus 1 times 4 times p plus 1. What is that? So remember I said that this is like the uniform mesh. It's just it has now 4p as its increments along its width. So that's why we have 4p here. Okay, so I minus 1 times 4p, when I is 1, this is 0. So plus 1 is just, we have 1. And then we have I times 4p here. So I times 4p is, well, exactly 4p. And well, let me actually continue so that we see the mesh we want to have. So okay, for this one we were at 1, right? For this one, p is, if I remember correctly, 4, no, 3. So 3 times 4 12. So this should be the 12th node. So 1 to 12. So nodes from 1 to 12 of the node list and all of its columns should be equal to the nodes of the first row of region 1. So let's check the index now. Again, we have I minus 1 times p plus 1 here. Why? Because this 4p is now p plus 1 for us. Okay, because we have p plus 1 nodes in region 1, remember? We have the diagonals. So p plus 1 times I minus 1, if I is 1, this thing is 1. So from node 1 of region 1 to node p plus 1 of region 1, which is node 4. So we take these 4 nodes, and then to it we add these 2 nodes of the second region. So for the second region, this was node 1 and this was node 2. Sorry, this is the fourth region, so core 4, 4. Now you will see that we have a very similar index here, but instead of p plus 1, we have p minus 1. Why? Because remember, for this one, we had p plus 1 nodes at every row. For this one, we have p minus 1 because we don't have the diagonals. Okay, so that is basically the only difference. So again, p minus 1 here. Okay, so this lets us take these 2 nodes. And then for core 2, 2, and 3, 3, so for core 3, 3, see that we have the same indices for what we had for core 1, 1, because again, they were similar in the sense that they had their diagonals. But now we flip this matrix. So so this is 1, 2, 3, 4. For the second region, this is also 1, 2, 3, 4. But we wanted to start from here, so that's why we flip this. And then for core 3, 3, we again have same indices for what we had in core 4, 4, but we flip it. Because remember, it went from bottom to top. So we flip it such that it goes like this counterclockwise. Okay. So this basically generates our node list for us. And then what's left is to generate the elements. Okay, so remember how we generated the elements for the uniform mesh. So we have an if condition that checked if we were at the very beginning of each row, right? Because we can plot it. Remember, to find the elements, so the nodes of these elements, we use the information of the first element of each row. So this, if j is equal to 1, it checks for whether it's the first first element of each row or not. And then using that information, we generated the other elements. We do a similar thing in void mesh. So we run that one. Okay. So we also comment these. Okay, So let's see. What's the difference? Well, first we initialize our element list as usual. So a number of elements, node per element. And we have two for loops. One is from I to m and one is from j, 1 to 4 times p. Why? Because as I said before, this is very similar to a uniform mesh that is just, its p is 4 times what it was. So we have that. And then we have two if conditions now. So the first one, as it did here, checks if the element we are looking at is the first element of the specific row. Okay, so then using the information of the first element, you will calculate the other elements. But the difference here is that we have a second if condition, and it checks whether this whether the element you're looking at is actually the end of the specific row. So these elements. Okay. The reason for that is because the end of this, when you think of this as a uniform mesh, the nodes at the very end are the same as the nodes at the very beginning, right? So this diagonal nodes. So because of that, we need to be careful when writing the nodes of these elements, because okay, let's actually see. When we're at, for example, node 2, we look at node 1. When we're at element 2, we look at element 1. So again, the first node is the second node, and the fourth node is the third node of the first element, and so on. And we can find the second node by adding 1 to the first node, and the third node by adding 1 to the fourth node. So this is what we do here. This is exactly the same as this thing. So it's just their indices here are different, and the only difference is 4p here, right? Because as I said before, this is like a 4p uniform mesh. So I won't really explain it much further, but so this is how we normally generate our nodes elements using the first element of each row. However, if you look at the last ones, they break the rules. So remember, for this one, this is the first node, this is the second, this is the third, and this is the fourth. So normally our second node is the first node plus 1. But now it's not like that. First node plus 1 is actually our third node now. And similarly, the third node is equal to fourth node plus 1 doesn't work either. So the only exception to this rule is, well, the first elements and the last elements of each row. So that's why we need to check for those. And then for the first elements, you can see that if you take a look at our uniform mesh function, again, there is really not much difference. So let me paste it here. So you can just see that our piece became 4 p's. Okay. And this p plus 1 here becomes 4p. Why? Let's see. So this thing is the fourth node. So we're looking at the first node. And to find the fourth node, we are adding 4p. Why is that? Because, well, 1 plus 12 is 13, right? So that's how it works. So these are the only differences. Our p's become 4p, and this p plus 1 becomes 4p. And the only thing that's left to check is if j is equal to 4p. So remember, for uniform mesh, j counted our columns, right? Again, j counts our columns. And if j is equal to 4p, we are at the very last column of elements. So at the end of each row. And now we need to write a new rule such that we can assemble our elements. So let's see. We take a look at our first node. And the first node is this one, right? So 1, 2, 3, 4. And for this one, it was 1, 2, 3, 4. It's the same as the uniform mesh. That's why I didn't really go into detail with these two. So the first node should be the last node of the first row of what I call row of nodes, right? So it's I times 4 times p, because we have 4 times p nodes at every row, right? Normally for the uniform mesh we would have 4 times p plus 1, but because our n nodes are the same as the starting nodes of every row, we don't have that plus 1. Okay, I think I didn't explain it very clearly when I said this. This 4p is, well, it used to be p plus 1 in the uniform mesh. It became 4p, right? And the reason is that, so normally if this were a uniform mesh, we would have 4p plus 1 nodes on every row. However, because our starting and ending nodes are the same, we have 4p nodes. So it's that. So as I was saying, so I times 4p is the end of our first row, or the ith row we're looking at. Okay, and so this is our first node of the element. And the second node, this one should be that thing on the previous row. So if, for example, if we're looking at the 24th node, it should be that thing on the previous row, so 12 plus 1. Okay. So because of that, we have I minus 1 times 4p. Now we had I times 4p. So I minus 1 times 4p brings us to the previous row of nodes, and we add 1 to that. So let me repeat. For the 24th element, this is the first node, this is the second node, right? Our first node is 24. We find it here. With I minus 1 times 4p, we go back a line, a row, so we're at the 12th node now, and we add 1 to it, such that we get our second node. And for the third node, what we do is, well, we say our third node is our first node plus 1. And you can see that that always works. So 12, 13, 24, 25. So here, what we had for the first node, we paste it here and we add 1 to it. And then lastly, for the fourth node, now we again take a look at the first node. So this is our fourth node, right? And we said there is just a row of difference between them. And we know that there is 4p nodes in every row, such that this I and I minus 1 logic works. So because of that, we add 4p to the first node of the element. Okay, such that from 12 we get 24. And as I said before, this else just is the same as our uniform mesh. Takes a look at the previous element and its nodes and generates the current element's nodes using those. And then this is how we generate the domain with the quadrilateral elements. So if we want to have triangular elements now, let me just copy this code as well so that we can compare them. And notice that they are exactly the same. So we're just dividing every quadrilateral element into two, as we did before in the uniform mesh. So let me undo that. And then let's change the element type and run it. And as you can see, we have the same number of nodes, but we get twice the number of elements. And this is how we generate the constant strain triangle domain. So that is all for this video. But I just want to comment on one thing. So as I said before, this is just one way of doing this. This is how I learned back when I took this course. So you can change it. If you can find a better or more efficient way of doing it, then that would also work. Why not? And in order to generate the different kinds of domains you are required to have in your project, you will need to develop your own rules. So you will have an inclusion, for example, and different types of inclusion. So you may have a square or a rhombus. So this is just something you can get an idea from and then build your own code on it. So I just wanted to mention that. And see you in the next video.